Chapter 22, Alpha Substitution Reactions. This is an aldehyde. We know this carbon is alpha carbon, the carbon bonded to the carbonyl group. The hydrogens on the alpha carbon are alpha hydrogens. Aldehydes always have one alpha carbon, so they have some hydrogens. This is a ketone. This has two alpha carbon. The hydrogens on them are alpha hydrogens. These and these are alpha hydrogens. What about them? Look here. Alpha hydrogens are slightly positive. They are positive means they are slightly acidic. What is the reason? Because the carbonyl group is an electron withdrawing group. It causes minus inductive effect. Pull the electrons in the bond towards it slightly. That makes it this carbon positive. In turn, it pulls the electrons from this bond. As a result, this becomes slightly positive. This is a ketone, same carbonyl group. It is an electron withdrawing group, but it causes minus inductive effect equally on both sides. That effect actually pulls the electrons from these bonds. So they become positive. The same here, it spreads over all the three. But if you compare the amount of positive charge, say, let me mark it as, so if you compare it, the positive charge, this one, will be slightly higher than the positive charge here. What is the reason? The carbonyl group pulls both the sides the same. That inductive effect is distributed over two hydrogens. Here it is distributed over three hydrogens. So less the number of hydrogen, it will be slightly more acidic than the more number of hydrogens on one side. How much acidic? We use pKa to measure the acidity. Most of the carboxylic acid acidity is around 5 pKa. The water's pKa, water is an acid, its pKa is about 15.4. Water is the weakest acid. This one is weaker than water. The acidity, the pKa of the alpha hydrogens are about 20. But if you take aldehydes, it has one set of alpha hydrogens they will be equally acidic because they are present on the same carbon. They experience the same amount of the minus inductive effect from the carbonyl. But it is not the case in the ketones. In this ketone, you have two, here also two equal, the same amount of inductive effect spreads on both sides and distributed over two hydrogens. So all these four hydrogens will be equally acidic. Look at this example. It has two alpha carbons. This one has only one hydrogen. This has two hydrogens. Same inductive effect on both sides. But this will be more acidic because it is less one. This will be less acidic of the two. So less the number of hydrogens on alpha carbon, higher their acidity. Why? I explained in the earlier slide. The inductive effect is the same on both sides. It makes the carbon positive. In turn, it pulls the electrons towards itself. As a result, the positive charge on carbon is distributed on both sides. So the same thing here. So these two will be slightly more acidic than these three because less the number. We will see some molecules in which alpha carbon may be present between two carbonyl groups, just like this. Look at the alpha carbon. Or a carbonyl group and an electron withdrawing group. Or even two electron withdrawing groups. We see alpha. Sometimes we see a molecule which contains the two electron withdrawing groups, say CN, alpha carbon. So the hydrogens on these alpha carbons will be more acidic because they are subjected to inductive effect from two carbonyl groups. So examples here, this alpha carbon has CH2. This is an alpha has CH2. Alpha CH3. Inductive effect, inductive. But this has two inductive effects operating on it, minus I. As a result, this will be most acidic of the three. Its pKa is about 10. And then this 3, because there are more numbers than this one, or least acidic of the 3. These two are simply acidic. If you look at this one, you have an alpha carbon here. Alpha, alpha, alpha. These have two hydrogens, same inductive effect, same inductive effect. on these two hydrogens. But this has subjected to inductive effects from two carbonyl groups. So these two hydrogens will be most acidic or more acidic, but these four will be equally acidic. In this example, these are alpha, this is alpha carbon, this is an alpha carbon. This alpha carbon is between a carbonyl group and which is an electron withdrawing group, and then another electron withdrawing group. But this is actually subjected to the inductive effect from carbonyl group, but this is subjected to influence to, so this will be more acidic, these two. This will be just acidic, less acidic. Because of the acidity, we are going to say something. If you take a beaker and dissolve an aldehyde in a solvent, add some acid, what will happen? This is acidic solution of an aldehyde. The carbonyl group has a lone pair. It will pick up the proton. I combine steps. And since the alpha hydrogens are acidic, one of them dropped down. This product we saw many times. It is an alkene and alcohol on the same functional group. So this is called the enol. It forms an enol. If you take the example of a ketone, ketone has two alpha carbons. This has three hydrogens. This has two hydrogen. Let me highlight one. The same way, the oxygen picks up the proton, the bond flips, and this flips, and H plus drops down. So this is an enol. I'm going to call it enol 1. The same thing is possible on this side. That is also alpha carbon. When this picks up the proton, this goes there, and this flips. So you get this enol. Let me call it as a enol 2. Since it has two alpha carbons and they have hydrogens, there is a possibility for the formation of two enols. Of the two, this will be the major. That means that this is minor. Its concentration is much less than the compared to that. Why? Of the two alpha hydrogens on both sides, this is more acidic. It is easy to drop. This is less acidic. It is harder to drop. So the reaction will go this way because it is easy to drop the proton and become an enol. So it is major product. If you take an aldehyde or a ketone and treat it with a base, what will happen? There are two alpha hydrogens on it. Let me highlight one. The base will abstract the proton from the alpha hydrogen, alpha carbon, because it is slightly acidic. And then this will become negative. The base becomes a conjugate acid. This one is called as a enol cation. If you take a ketone, as we saw in enol, the same thing will happen because you have two alpha carbons. This has two hydrogens, and the base will abstract this one and flip the bond. You get this enol cation 1. The same thing is possible from this one. It has, so if the base abstract the proton from here, so this will go there and form an enol cation. Let me call it enol cation 2. We can use the same argument. We used it for the enol. This will be the major of the two. That means that this will be minor of the two. The reason is it is more acidic. It is easy to pull it from there. But here CH3 proton is less acidic. It is harder to abstract it from there. The enol cations normally resonate. This is an enol cation. It resonates and flips it. And then it can come back and flip it here. So you can write the enol cation as shown as an A or as a B or both. If you look at the formation of the enol cation, we used it. It is an acid-base reaction because aldehyde or a ketone, we use it as a substrate, loses the proton and becomes a conjugate base. The base subtracts the proton, becomes a conjugate acid. So it is an acid-base reaction. For this reaction to happen, we learned in chapter 2, this acid's pKa, conjugate acid's pKa, must be greater than pKa of the aldehyde or a ketone. We used it as an acid. So what kind of the base we can use then? Wow. What is this girl doing? She pulled her teeth. And show it to you. Because her teeth was shaking. It was easy to pull it. Most of our teeth are not shaking now. If we had to pull it, we had to go to the dentist. They had to pull it with the pliers because it is harder to pull the strong teeth. The same thing is possible in this case. We have to, because these are not highly acidic. These are very, very weak acids. If you want to pull the hydrogen or proton from this one, we have to use a strong base. What strong base we can use? We always use the hydroxide or alkoxide. Examples, sodium hydroxide or potassium hydroxide. As a strong base, in this OH minus is the base, we know. We also use the alkoxide, for example, CH-3, O minus, Na plus, or ethyl, say put a potassium there, ethoxide. In this is the base, this is the base. Can we use them? Let us try. If you use the OH as a base here, if it abstracts the proton from here, the conjugate acid is the water. Its pKa is 15.4. But here we saw the pKa of this one is about 20. So which one is a strong acid, the aldehyde or a conjugate acid? This is a strong acid. Reaction will not go from weak acid to strong acid. So this reaction will not happen. If it happens, it actually very small amount of the inert ion will be formed. What if we use alkoxide in the place of it? So say sodium methoxide. It is also going to pull the alpha hydrogen and make it into an inert ion. And this will become CH3OH is an alcohol. The alcohol's pKa is about 15.5. So this is also, actually, if you take this is a 15.7. So this is a stronger acid. Than the aldehyde, it is a weaker acid. The reaction will not happen. If it happens, the amount of the inert formed is very, very little. What to do then? Look for some strong bases, stronger than hydroxide and alkoxide. We have three candidates. One is the sodium hydride. In this Na plus, H minus. So this acts as a base. The other one is a sodium amide. In this is positive, this is negative. This will act as a base. The third one, lithium diisopropylamide. We shortly call it LDA. In LDA, you have this is the base, it is a counter ion. But if you compare the LDA with others, LDA is a larger base, bulky base. This is not. H minus is not bulky. So if you use NaH, the base in this case is a H minus. The H minus is a base. It will come and abstract the proton from here and flip that and make it into this. So the conjugate acid is hydrogen. Its pKa is 72. The pKa of this is 20. So this conjugate acid is much weaker acid, much weaker acid than aldehyde. So this reaction will happen. If you use NaNH2, the NH2 minus is the base. So it will abstract the proton from here. And this will be, the conjugate acid will be ammonia. Its pKa is 36. So this is much weaker acid than aldehyde. So this reaction will happen. If you use LDA, in LDA, you have two isopropyl groups. I write it this way. That is a negative. It pulls the hydrogen from it. So this one is going to be the nitrogen with a two isopropyl group. This is a conjugate base. The pKa of this is also 36. The pKa of the aldehyde is 20. So this is a weaker acid than the aldehyde, so the reaction will happen. There is a word about using LDA. If I use the NaNH2 as a base, there are two alpha carbons in this one. These are hydrogens. This alpha hydrogen is more acidic than the other two. So it can abstract the proton from here, or it can abstract the proton from here. If it abstracts the proton from there, you get this one. This is a enolate ion. If you abstract from here, you get this enolate ion. We said it is actually, this will be major, this will be minor, for the reasons I explained here, because it is more acidic, easy to pull up. But if you use LDA, the same two will be formed. But this will be the major, this will be the minor. Why? LDA is a bulky base. It finds harder to go closer to this and pull it because there is a CH3 that is sterically hindered that hydrogen. So if it pulls, it is only a smaller percentage. It goes to the less acidic one and pull it, so it is a major product. We are going to compare the enols and enolate ions and the relative reactivities. I use the standard, the alkene. You see, alkene has a double bond, enol has a double bond, enolate ion has a double bond. If you put an electrophile, it will pull it. I'm sorry. So if you put an electrophile, they'll pull it and bond with it. Here also this is possible. So this is actually when it is pulling it, breaking the bond, this flows in. This case also, this is happening. and this comes here. But if you compare them, the alkene actually breaks the double bond and bond with the electrophile. The same thing in enol and enolate ion. But enol help comes from the OH. But here it is free-flowing electrons sitting there. It flows in, so it is more reactive than enol, which is more reactive than alkene.